Hello and welcome to this video that goes through questions 12 to 15 of the AQA Further Maths Level 2 Specimen paper, paper 1. So the next question is prove that tan squared x minus 1 is equal to 1 minus 2 squared x divided by cos squared x. So this one is quite a tricky question to do. The first thing that I would do here is probably rewrite tan, because I know one of the rules. We know that one of the rules, tan x is equal to sine x over cos x. So here if we square both sides we get tan squared x equals sine squared x over cos squared x, and therefore we can substitute that in, so it becomes sine squared x divided by cos squared x minus 1. And then the goal here is we're always trying to get to this as a goal, so you should always, if you're stuck, you should refer back to it and think how we can get to the next step. So here, notice that the denominator is cos squared x. So if we times minus 1 by top and bottom by cos squared x and then times cos squared x, we're going to get the left hand side where sine squared cos squared, all and with a denominator of cos squared x. So this becomes sine squared x over cos squared x minus cos squared x over cos squared x, which we can put together as sine squared x minus cos squared x divided by cos squared x. And then from here what we can do is we can say that we don't have any sine squared terms in our numerator on the top, so let's replace the sine squared x. So we can use the identity sine squared x plus cos squared x equals 1. So sine squared x equals 1 minus cos squared x. Then we can substitute that into our equation. So that becomes 1 minus cos squared x minus cos squared x divided by cos squared x. And then minus cos squared x minus cos squared x is minus 2 cos squared x. It's 1 minus 2 cos squared x divided by cos squared x, and that gives you your final answer for this question. Question 13a, work out the coordinates of the stationary point of the curve y equals x squared plus 3x plus 4. So the first thing we want to do is we want to differentiate our term. So if we differentiate, remember the rules for differentiating is we times by the whole power. So if we had y equals a x to the n, then dy dx is equal to a n x n minus 1. So from here, if we do the thing times by the whole power, so it becomes 2x, then 2 minus 1 is 1, and then 3x just becomes 3, and 4 goes to 0. If it's a stationary point, then dy dx must equal 0, so we say 0 is equal to 2x plus 3, and then we rearrange, we say it's minus 3 equals 2x, and it's going to be minus 3 over 2 is equal to x. So our x term is minus 3 over 2, so we could substitute that into part of our answer. And the second part we need to find the y coordinate, so y is now equal to minus 3 over 2 squared plus 3 times minus 3 over 2 plus 4. Minus 3 over 2 squared is equal to 9 over 4. Minus 3 times minus 3 is 9. 2 times 2 is 4. Minus 9 over 2 plus 4. And then from here we want to convert. So let's times this one by 2, top and bottom by 2. So we get 9 over 4 minus 18 over 4 plus 4. So that gives you minus 9 over 4 plus 4 minus 9 over 4, and we want to convert, so we can say that this 4 is equivalent to 16 over 4, so it's minus 9 over 4 plus 16 over 4, which is equal to 16 minus 9, which is equal to 7 over 4, and that would be your answer here, 7 over 4. Just double check that is not answer. Yep, so that's fine. And then explain why the equation x squared plus 3x plus 4 equals 0. So for this one we use the discriminant. So the discriminant is b squared minus 4ac and if it has no real solutions, it must be less than 0. So we substitute in. So again, of A, B, and C is the coefficients. Essentially, A is the coefficient of x squared, B is the coefficient of x, so the number in front of it, and C is just 4. So we plug this in, it's going to be 3 squared minus 4 times 1 times 4, which is equal to 9 minus 16, which is equal to minus 7. So therefore, b squared minus 4ac is less than 0. So therefore, there is no real solutions. And that is it for 13b. Then question 14. In the diagram, DCB is a straight line. Work out the length of DC. Actually, to go back to this one, I think you need to I don't think that this is enough for the 2 marks. I think you have to explain why we use b squared minus 4ac. So here, if we go back to the quadratic equation, it's minus b plus or minus the square root of b squared minus 4ac. So the fact that you should add that there is not possible to get a negative surd or negative real surd. This becomes a complex surd, which you'll look at in further maths in A level. But yeah, that's probably you have to add that little bit extra information in for the explanation part. It's not good enough, I don't think, to say that it implies no real solutions. Although in A level maths that would be a good enough one. But for this one, you have to explain where you get the b squared minus 4ac from. Question 14. Work out the length of DC marked x on the diagram. So for this one, work out the length of DC marked x, write your answer in the form a minus root b. Okay, so we know that, okay, so we've got 2 right angled triangles here. We've got our first one is this one, which is 45 degrees and 3 root 2 and 90 degrees, and that means that we can find some of the shapes. So this is D, B, and A. So from here we can find, let's call this one A. Well, actually, don't do that one because that's part of the answer. Let's say it's X, and this one is, oh no, because X is the, so let's try and find a number. So let's say this is F, and this is G. So here, for using trigonometry, so SOHCAHTOA, this is the hypotenuse, and this is opposite. So I know that sine 45 is equal to F over 3 root 2. So sine 45 is equal to 3 root 2 sine 45 is equal to F. And then to find sine 45, we can use the your fingers to find this out. So essentially, if you've got your hand in front of you, actually, you need your thumb and then your fingers. No, oh, sorry, this is not looking very good. So the way that I do it is, you have your thumb up like that, then you have your fingers, and then you use the method to determine which one it is. So this one is 0, this one is 30, 45, 60, and 90, and you close your middle finger off, and it's the top 2 numbers divided by, so it's the root of the 2 fingers above it, so it's going to be root 2 over 2, which gives you the correct form of sine 45. So it's the fingers above that one, so you cross this one out, and you've got 2 fingers above, so that's going to be root 2 over 2. If it was cos, it would be actually the same, root 2 over 2, but below. So sine 45 is root 2 over 2. So we plug this in, so 3 root 2 over 2. This is equal to 3 times 2 over 2, so it's equal to 3. So we know that F is equal to 3. And then we also can find G. So G is equal to, so it's going to be cos, so G is equal to, so it's cos 45 is equal to adjacent, which is g divided by 3 root 2. So it's 3 root 2 cos 45, and cos 45 and sin 45 are the same. So that is also equal to 3 root 2 over 2, which we know is 3. So now we have an equation. So on our triangle now looks like this, with 3 root 2, 3 and 3. Now we can do our second triangle, which is a bit smaller. So this one is going to be a triangle with 60 degrees. And then we have, so we don't know what CB is, but we do know that the length of this side, F, is equal to 3. So here we can find, we want to find the length of DC, so we should find what CB is first. So let's call this one M. So to find M is going to be tan 60 is equal to 3 over M. And then we rearrange the tan 60, so it's going to be M equals 3 divided by tan 60. Now to remember tan 60, you can still use the same one, so remember that tan x is equal to sine x over cos x, so it's equal to sine 60 over cos 60. To find out what this one is, again, this time we're going to use the 61, so sine 60 is 1, 2, 3, so it's going to be root 3 over 2, and cos 60, it's only got one finger below the 60 degree one, so it's going to be root 1 over 2. So this ends up being root 3 over 2 divided by a half, and then root 3 over 2 divided by a half is just equal to root 3. So if we go back to this one, M is equal to 3 divided by root 3, and that gives us our equation at the bottom. So now we want to find what DC is. So we don't know what DC is, but we know that the whole length is equal to 3, and we know that the bottom one here is going to equal BC is going to equal 3 over root 3. So our answer for DC is equal to 3 minus 3 over root 3. But this isn't the final form, so we need to rationalise the surd at the bottom. To do that, we can times both top and bottom by root 3. So that's going to be equal to 3 minus 3 root 3 over 3, which is equal to 3 minus root 3. So your final answer is simply going to be 3 minus root 3. Okay, let's have a look at question 15. A, B, C, D are points in the circumference of a circle such that BD is parallel to the tangent of the circle at A. Prove that AC bisects angle BCD. Give reasons at each stage of your working. So this one is a very difficult question. So what I would suggest is go through the circle firm rules that you know that might apply here. So first of all, always think about your goal. Your goal is to get these two angles equal to each other. That's what the bisecting of the angle is. So our goal is to get BCA is equal to the angle of ACD. Now, the way that you would probably need to do it is to an intermediate angle. It is unlikely that you're going to find a way that they're both equal to each other directly, but you can get them equal to an intermediate angle, and therefore you can probably show that they're equal. So to do that, we're going to have a look at various ones. So the obvious one here is we've got the tangent rules, but they're unlikely to help because we don't have any values here. So, and using 90 minus values is not very helpful if we don't have any numbers at all. So I'm going to rule out the tangent ones here. If you had some numbers here, maybe that would be more useful. One thing that I've noticed is the parallel lines. That suggests that we could use the parallel line rules here. And what I'm struck by is this one here and this one here is going to be equal to each other through the parallel line rules. So that's going to be angle EAB is equal to angle ABD, and that's through the alternate angle rule. Okay, so alternate angle rule, which states that they are equal. So that is just using parallel lines. If they give you something like parallel lines, it suggests that we're going to use it. We also have this one here that should be the same, which is going to be angle, so we know that angle DAF is going to equal angle ADB through that rule as well, and that's for the same rule, so alternate angle rule. I should write this out in the actual exam properly, so that might be useful to us. I'm also interested potentially in the alternate segment rule, because I've got a lot of chords and I've got a tangent. So it's got a tangent as well. The rule that people are scared of using because it's quite difficult but is likely to be, if it definitely has no numbers, is that the alternate segment rule that states that if you have an angle between the tangent and a chord, then the other angle of the triangle that chord forms is going to equal it, so on the opposite side basically. So A equals B, and that will be in the alternate segment theorem. So here, if we look at some potentials in the alternate segment theorem, there's quite a lot going on here. The first one that we could look at here is, so A, we'll do a different colour. So we do A EAB, which is this one, and then we can make a triangle here, and that links us to our first angle that we are interested in. So we have linked together angle EAB is equal to angle ACB, and that is using the alternate segment theorem. So that means now that we have linked, so we linked a couple of it to one particular angle, which is this one here. Now this angle is also linked to this one, and we can see here that this is also going to be, oh no, so it's not going to be that one, but we can also use another rule, which is the angles in the same segment rule. Because, okay, so angles in the same segment rule, the reason why I'm thinking of that one is because there's a lot of triangles on here. So if we go through the angles in the same segment rule, if you have a chord and you have two values that go off that, so two lines that go off that chord, those angles here are going to be equal. So this is, so x and y, x will equal y. And what I'm looking for now is, I'm looking at this angle here, because I know that it's equal to the yellow one, with this angle, the red and the red are equal to each other, and that's equal to this one here. So if I can get this equal, and I notice that there's a chord here, and it has two lines going off each of it, and this is where we're going to get our answer. So notice here that this makes this triangle of that chord, and there is also the same chord, so another triangle coming off the same chord, and therefore this angle equal each other. And we have now solved our question, because now angle ACD is equal to angle DBA, and that is through the angles in the same segment. And then from there we can just say, well, so therefore BCA, so angle BCA is going to equal angle ACD, and that's just through the fact that, so again, if you've got different colour pens or pencil, really, or like even number the angles so you know which ones they are. So no BCAA equals ACD simply through the fact that we know that we know that EAB is equal to DBA and also equal to BCA. So we know that that angle here is equal to that one, but it's also equal to this one, and this one has been proven equal to ACD. Notice that we didn't use this one in our answer. It doesn't matter if you have an extra proof, you're not sure. But yeah, that gives your answer. So therefore, AC bisects angle BCD. A very difficult question, but if you can get this one, then that's fantastic. It's very hard. Just take your time with it. Come with as many theories as you can. Write them down. You get them marked, so picking them up. That is the most important thing. So even if you didn't get all the way through and you couldn't get the last one, you can still get 2 marks for the question by just writing down different theories. Go through the different theories, redraw out your question if you need to, just focusing on various theories for this one, but this is a very difficult question. It's one of the hardest circle theorem questions I've seen. Okay, if you have any questions, please let me know.